Okay, oh, all right. I'm gonna introduce myself then. Thank you for the organizer, definitely, for inviting me. And this is like a great opportunity for me to like present my work that is just published like 2 months ago in December last year. So this work is in collaboration with Natapong Wonangkorn and my student from Thailand, and also Howard Weisman, who is already here. And then, so I was working on this project when I was a postdoc in Australia. And then now I have moved to Thailand and work as a faculty position there. So I'm actually from Thailand. And so basically I'm going back to my home country. So if you ever want to visit Thailand, contact me. I might try to like organize, yeah, you. It's a beautiful country. So it's a great place to visit. So this talk would be really similar to what Anton's gave a talk, I don't know, like last week, I guess, but in a different perspective. So it is a little bit funny that I prepared a talk and then I went to watch his YouTube video and I was like, why are we thinking the same? So this talk would be kind of having the similar story, but it will be a different kind of perspective. So hopefully you will learn different things from here. So in this talk, I'm gonna convince you why the higher order unraveling would be useful, and then how we're gonna do it, and then what we do it, and then what's the criteria of what we think as a good and higher order and high accuracy unraveling of the Lindblad master equation. And then we will also talk about the application and how it can be useful in like parameter summation in that case as well. So let's start with this slide. I'm not going to talk so much about it because it's basically related to the title of this program, Quantum Trajectories. And there are so many people have done the introduction of it already. I'm going to point out something that many people associated the quantum trajectory with a stochastic master equation, where you have seen this equation probably so many times with the unitary terms and then the coherence terms and then the measurement back action term. And this measurement back action is in terms of the Wiener process or the Wiener increments. And then the Wiener increments can be generated like numerically, or you can think of it as some kind of approximation that you can get it from the measurement record. Like, for example, like the YT would be the measurement records, and then this term would be the information that you gain from doing the measurement. So my point of this slide is to say that my kind of view of quantum trajectories would be mostly on the continuous measurement of the quantum system. And then in this case, I'm going to focus on the diffusive type measurement. There's a jump type, but I'm not going to talk about it today. So this picture, you have seen so many, what is that, version of it. And here's my version of this. So you can think of the system, which is like in the pink one, get coupled to the bath, and then once it coupled, it get detected, and then get the measurement result Y1, Y0, Y1, and Y2, and so on. And then one thing that I want to point out is that you can see that each of the baths are separate things. So there are like initial conditions of like each of the coupling. They are separate baths. They are not correlated. And that's like the strong Markov assumption that we have to use in order to derive the quantum trajectory for this case, for non-Markovian, for Markovian case. So once we have these measurement results, we can plug in some equations to be able to find the trajectory of the quantum system. So today I'm not going to talk about the math so much, but I want to focus on like how the theory of quantum trajectories can be applied to experiments. And I was actually lucky when I was in PhD. It was like an early time when people are looking at like superconducting qubits experiment. And then in a superconducting experiment, it turned out that the time scale are perfect in such that you could do the continuous measurement, and then you could get the signal, and then do the like kind of use the SME or using some theory of quantum trajectories to translate the signal into the state or the evolution of the quantum state that you are interested in. For example, in this picture would be the example of, actually it's from Kater Mersch, who was a speaker in this conference as well. So this one is a superconducting qubit in the 3D cavity. And then you could do the measurement by probing the microwave in the cavity and then come out and then do the homodie measurement or like some kind of amplifier. And then you get a signal come out as like really, really fluctuating signal. And you can get this signal, plug it in the quantum trajectory theory, and then come out to the quantum trajectories and then say that we can compare between the theory and then the experimental data, which could come from there's a technique of doing the tomography and then do the comparison between the theory and experiment. So you can see that the match are not perfect, but it's actually good enough that it can be like, it's a good verification that we have a nice theory that can explain what is going on in there in experiment, right? So the two examples that I want to focus on this talk would be the qubit stat measurement, which is like measurement in 0 and 1 basis, and then the qubit fluorescence, which is looking at the decay of the excited state to the ground state. So this is the example of the experiment that was from Benjamin Howard, which is also the speaker of this conference as well. So because I was working with experiment at some point, I found a common problems that I think it's really interesting, and then we haven't solved it completely yet. So what's the problem? The first thing, SME, stochastic master equation, we always take the limit of dt goes to 0. Why? Because it's, well, because you want the differential equation from it, and that's the limit that you have to take. So the dt is small, and you can take the eta rule, the dw squared is approximately dt. So that means the dt has to be small, right? But what about an experiment? Can you actually probe the system at infinitesimal time? And the answer is like, no, you can't. Because of what? Because like, let's say that you have the cavity coupled to the qubit. The cavity has like a decay time. It's a finite decay time. Microwave comes in and interact with the qubit and comes out to the detector. It takes some time, and that time is finite. So if we are really forcing to, let's say that probe the qubit really fast, making the dt to be like really tiny, what happens is you will get the signal that definitely the Markovian assumption will break down because the bars are all correlated, right? It's not a separate bar that coupled to the system anymore. And then the second one is like the noise that you come out, or the signal that comes out from the detector would be not just like simple Wiener process or Gaussian white noise anymore. It will be a color noise with like non-flat spectrum. So the reason that so far people have been doing quantum trajectories and experiment is that they will try to approximate or say that this one can be minimized by saying that, well, just integrating the signal long enough so that it's long enough for the cavity to decay, or the Markovian process can be still valid, and the noise can still be roughly the white noise. So the easy fix is to make the dt large, right? So now, if the dt is large, we cannot use the SME because SME taking the limit of dt goes to 0. So there's a lot of problem coming up if you are using the SME to process the experimental data. For example, like state might not be positive, it can be outside of the Bloch sphere. And then I think many people who have done this before know this problem. And so there are a lot of fixes, and then the approach that try to solve this problem. Definitely, I'm gonna throw away the SME first, for sure. And I want to focus on the Krauss map or Krauss form, which is like having to try to find a map of the K and then calculating this update equation, plug in the measurement results, and then come to the state update at the next time step, and so on. There are like many approaches here. So I'm going to kind of go through many of this and then see which one is actually good and how good and they are. So the first one is the conventional approach. I'm going to call it Ito approach. It's the most connection to the SME equation. And then the second one is the Rochon-Roth approach. If you're interested in this approach, you could look at their paper. And then the third one is the Guevara-Weismann approach, which I will talk about it more in detail. And then the last one is that I'm going to propose a new one, which is like the higher order, and then hopefully I'll convince you that it solves a lot of problems here. So before I say that which one is good and why, I would like to set up the basic ground of what I think should be the criteria for a quantum trajectory map. So think about this quantum system, get a measurement, you get a measurement results, and then you can do an average to get some kind of average trajectory. So I would set the first one as the first, like the strongest condition. So the strongest condition is, let's say if I have an access to the really, well, let's say really tiny signal, and then use that like, sorry, not tiny, the signal with the infinitesimal time scale. And I use this signal to calculate the trajectory using any map. You could use SME, and then you get trajectories. I'm gonna call that true trajectory or exact trajectory. And if I have a map that with the delta t, one thing is I'm going to differentiate between dt and delta t. So dt would be infinitesimal, and then the delta t would be the coarse grain finite t, finite step. So if I have a map with a delta t map, and I calculate this trajectory, and then if that trajectory reproduce or exactly match with the true trajectories that was generated with the tiny time scale, then I would call it like satisfy the first condition, which is like a valid quantum trajectory. That's just the strongest one. And then if I have this, many of you probably know that if you take an average of them, of many trajectories, infinity ensemble of it, then you will get back the Lindblad equation, right? And then when I say Lindblad, I'm not saying just the first order in dt. I'm saying that the Lindblad, in this case, should be the infinite order of like the Lindblad here, which is an exponential of delta t times the L operator. Okay, so in this case, I can show you that, let's say that if you expand it to the second order, this is something that you might have seen. It's very common. But if you expand it to the second order, you will see that there's another term, right? A d square, and then keep going to the third order and so on. I'm gonna stop at the second order here. Oh, sorry. And then, so these two are the strong condition, but usually many of the map, we don't have that. So I'm gonna introduce another, like the third or the weaker condition, which is called valid average quantum evolution, which at least like if it doesn't exactly match with the true trajectories or like infinite order of the Lindblad, at least it should satisfy these three conditions. The first one is complete positivity, second one convex linearity, and then the third one is the trace preservation. So I'm gonna use these conditions to check the operators that I have introduced. So the three conditions, I think I don't have to say much. Complete positivity is like acting positive state to positive state on the bipartite quantum state. And then the convex linearity is linear map from the weighted mixture of two states into individually mapped states. And then trace preservation is related to like the norm. You map the trace one state into the trace one state. So now we have these three conditions. How am I gonna check these three equations? So it turns out that even just the word average has been, what is that, like defined in so many ways. And I'm going to show you there's like three methods so far that I have seen in the literature that are used in averaging the trajectories. So the first one is probably the most common, is that you average the trajectory with the correct probability. So the probability can be derived from the Krauss operator. I think that's the properties of the Krauss operator in this case, or the POVM if you are more familiar with that. So these trace of like K rho, K dagger would give you the probability of the measurement outcome, R, right? And then you use that probability to weight the states. So here's the state, right? State update from the Krauss map. And then you put an average with a weight here. And then you can see that they're canceled, right? And then you get the form of the average Krauss map, which is like the usual way. And then this is like the average state in this for the method 1. And so with this method 1, it turns out that it like satisfies the first one, complete positivity. That's automatic because it's in the cross form, right? For the second one, it's linear because, yeah, it is linear. It's clearly a linear function in row. And so it satisfies the 2 conditions on the top. But what about the third one? We don't know. So we have to check for the trace preservation, we have to check this condition, whether it match perfectly with the identity. So this one is like similar to the closure relation for the Krauss operator. Okay, so that's a method 1. So I hope you can imagine what is the method 2 could be, and it's really common in the simulation. In a simulation, we might not be able to generate these probability distribution, but we would do it with like a Gaussian approximation of it. They're not the same. This is the thing. So we can come up with some simple guess of the readout probability distribution. I'm going to call it rho G, PG. And then this one can be anything. It can be, the mean can be anything, and then the variance can be anything. You can come up with it. And then use this to calculate the average, right? Okay, so what's the condition here? The first one, yes, for sure. It is in the Krauss form. The second one is trace preservation, because if you trace on the right-hand side, you get this as like a 1, right? And then integral of any Gaussian probability would be 1. So that's automatic. So you get C1 and C3 perfectly. And what about the second one? Yes, we have to test whether it's convex linear only if these two are proportional. Or you could say that if you average it and then you get a linear function of rho, that means it's satisfied. Okay, last one, really easy. If you are using the stochastic mass equation, you're just generating the Wiener process and then just plug in the equation, and then you get the state at the next time step, right? And then this one, if you do an average, you know that the Wiener process average to what, 0? Yes, so that is just as simple as like the last term goes to 0, and then you get the normal first order Lindblad equation. So this one, definitely not complete positive. Yes, that's what I say. But then it's linear, it's convex linear, and also trace preservation. So it satisfies these two, but not the top. But I'm not going to talk much about this third method. So I'm going to compare these 4 with the idea that I have the signal, infinitesimal signal, and then integrated idea of it is like cos grain to get like the big Y. And then I'll use these 2 methods to find whether it matched the condition or not. Okay, I think it's good. So let's start with the first one, the Ito, or the simplest conventional map. I'm pretty sure that you have seen this map before. This map was written in terms of delta t and delta t. So maybe you have seen it with the dt, because dt takes to infinite order. Oh, sorry, infinitesimally small. But let's say that I just force it. I'm going to use it, and then just replace dt into delta t, and then just use this map for whatever my quantum trajectories. And because I want it to be normalized, and so you need this ostensible probability, and then many people use the Gaussian function for this. I'll explain it later, that there's a way to explain that how this come out also. And if I use this and then compare the 2 methods, we calculate this, the closure relation, and then find, as you expect, you will get not a 1, not exactly identity. So it only satisfies the C3 condition to only order and dt. For the second one, the second method, so here is a Gaussian probability approximation for this Ito method. So you can see that the mean is just the, what is that? The informative part of the signal. And then the variance is actually tells you that this is like the white noise, right? So basically it's like a similar to the white noise, but shifted mean to the informative part of the state, or something that you want to measure. And also it gives the C2 condition to the first order in delta t. And we also check that for the B condition, which is the Lindblad, the one above the C, it's also satisfied only to the delta T case. Okay, what about the second method, which from Ruchong and Ralph approach? So these map, maybe you have seen it before, but then I want to point out something. The difference between the Ruchong and Ralph approach is that it has an extra term on the right-hand side, which I think if you know the Ito rule, if you take the Ito rule or Ito limit, then this term would go to 0 when the dt goes to 0. So this one turns out that it has some effect on the map as well. You cannot just like simply throw away when delta t is finite. So we look at the method 1 and 2. And then here we can see that the trace preservation or the closed net relation has a delta t square, and then also has a delta 3 to the third as well. And then for the method 2, it's similar to the Ito case. The Gaussian approximation is very similar. And we always get the C2 condition and C3 conditions to satisfy only to first order in delta t, and also the B condition. I'm just going to go through it quickly. So Ito and Ruchong also both just to first order in delta t. What about the third one? Why do Guevara-Weisman have to come up with another map? There's so many maps already. So the reason is that because they want to fix the problem of complete positive, or basically this idea, the closer relation, they want it to be correct up to delta t squared. And so they come up with this another term, which is added to the normal Ito map. And I would say that this one is arbitrary. Yes? Yeah. Well, it's arbitrary in a sense that, well, if you add this term, this second order in delta t disappear. So that's the idea, the motivation behind it. And so this one, it satisfies the C3 condition to the delta t squared. And then on the right-hand side, for the method 2, you could see that the Gaussian approximation is also modified by another correction term that comes in a delta t squared. So how this one can be derived is actually derived from the probability from the method 1. So basically, in Guevara-Weisman approach, they try to match between the two to at least the second order. Make sure that the probability from the method 1, which is the trace of the Krauss operator, would match at least to the second order to the Gaussian approximation. Okay, so that's an idea. And that's why it gets the same solution, the C1, C2 and C3 conditions. And so in this case, C condition is satisfied to second order in dt, and delta t, sorry. But then the B condition, which is a Lindblad, is still in the first order in delta t. Okay, right. Now you probably see that what's going to be the next, right? I want to fix this. I want to fix this. I want to make this one to the second order in dt, which is kind of trivial, maybe. But we got a motivation how we do it. So the motivation for our work is from not the mathematical point of view, but from the physical model. So we go back and start from the physics from maybe the system coupled to the bosonic path. And we want to derive the Krauss operator, in this case, for the infinitesimal record for now. That can be derived in terms of this form, the initial. So the U is the interaction between the system and the bath. And it can be written in terms of the exponential of the C and dB. So dB would be the operator for the bath for the infinitesimal time. So with these U, and the initial state was assumed to be the ground state or the like vacuum state of the bath. And then the measure state or the projected state, basically you project the detector state at the end. You project it on the eigenstate of the homodie measurement. So this Y is an eigenstate of, let's say, this is like an homodie observable. So the homodie observable in this case can be written in terms of like dB plus dB dagger. It is similar to like A plus A dagger, which is like the X quadrature of the field. Yeah, and then this is the properties of the operator dB. Okay, so using this, expand it to, let's say, second order in dB, and then use the eigenstate of the quadrature operator, which can be written in terms of the harmonic, basically is an eigenstate of a harmonic oscillator. And then we find that once we plug this in, and then it turns out that what we get is just something in a similar form that you have seen it before. The first three terms are the Ito assumption. And then the fourth term are the correction from the Rochon method, actually. So it's really beautiful there. And then also this term, which is the product of the ground state, like the ground state and the eigenstate of the homodie. Turns out that it's just a Gaussian state, which is the Gaussian function that has been used to normalize the Ito map. So I'm going to use this to second order in dt, and then I'm going to do something different. Because now we are using the infinitesimal record, right? And then we are integrating over time, delta t, because we are coarse-graining the measurement record. So we have to multiply these little m together, and then take the limit of m goes to infinity, and dt goes to 0, and this is fine, right? And then it turns out that multiplying this together, taking the limit, everything perfectly, and keep only to order of delta t squared, we get this term. Well, it looks quite dramatic, but well, not too bad, right? So there are like, you can see some terms that's similar to the Ito one, which I think this one, and then that one. And then like some of the Rochon terms show it here and here. And so there's only two extra terms that are additional to the previous methods. And the rest are the same, the form of the cross operator, and with the ostensible probability, it's still Gaussian and so on. Okay, so now let's check the properties of it. As you expect, yes, it satisfies CT condition, and it satisfies C2 condition to the second order. And then also it satisfies the B condition, which is a Lindblad condition, to the second order in DT as well. Okay, what is next? So I have convinced you that we have proposed a new one, and then it fits the criteria, or the B and C criteria, to the second order in delta t. But what I'm gonna introduce you next is, what about the condition on the first one, which is the strongest condition? And I'm gonna show you that I haven't done anything strange, but it turns out that it's actually the best for the first condition as well. So I'm gonna call this one KW, and then W is from Bonglakon and Weizmann, but not Chantasri. Because like this is a democracy vote, right? There's a 2 W and 1 C. Okay, so how are we gonna do the valid trajectories to infinite order? We need to have a true trajectories, right? Come from somewhere. So it turns out that there is an exact map that we can show that it fits all the conditions to infinite order in delta t, infinite order in delta t. And this is the first one, is a Z measurement. It turns out that's like quite beautiful. The cross operator for Z measurement is in terms of the eigenstate. You can write it in terms of the eigenstate, and then with the square root of the probability, in this case, can be approximated as a Gaussian function. And then you can show that this one satisfies all the conditions to infinite order. I'm sorry about the Gaussian function here. It's not super Gaussian, but I wrote it by hand. So it's good enough. But this is for the qubit Z measurement. And so the measurement result is distributed in the Gaussian distribution around the eigenvalue -1 and +1. For the second example is a fluorescence measurement. It turns out that you can solve it exactly as well. And the map for the qubit fluorescence is in this form, where it is in terms of the X, which is some kind of filter record. So remember the YS is the infinitesimal record. And then you fine grain it with a particular filter function. In this case, it's an exponential filter. And then you get the X. And then if you know this exactly, the XT, you can put it in this map, and then you can get exact trajectory as well. But because we want to do analytically, and it turns out that integrating this one with the exponential filter is really difficult. So we're going to expand it to just second order in DT, because we only focus on second order in DT for now. And then if we do that, we find that it turns out to be in terms of the YT, which is the normal integral of the infinite record. And then this one is like another kind of filter function of the infinitesimal record as well. Okay, so just a little bit of short summary is that we try to find the average trace distance. We didn't look at the fidelity, but we look at the trace distance in this case. So we calculate the exact quantum trajectories here. And then the coarse-grained trajectories from like the 4 maps that we have. And then looking at the distance between 2, and then also average over all possible measurement record, because it should depend on the measurement record, right? And then also average over the initial state over like the Hilbert space. In this case, it's just qubit, and so it's quite easy. So we do this, and here's the result. Let's just focus on the bottom one. So it's like the smallest one among the 4, right? But we'll show this number again in the next slide. Okay, so we did analytic approach. We also going to check the numerical result as well. And then we did, like in this picture, this one is the, let's say I call it true record, which is the record that generated with like a tiny infinitesimal time. And then we coarse-grain it 100 times. So you see that the delta t is like -4, and then, sorry, dt is -4, and delta t is -2. So it's like 100 times. And then, so this is the coarse-grained record. And then use this coarse-grained record to calculate the trajectory. So you can see that the trajectory is for the blue one, which is a true or the exact one. And then the orange one are not exactly the same. It's like one of them is the smooth function of the other one in a sense. And then we can use different methods to calculate the trajectories. This one is nothing, just to test that there are, just to say that all of the maps are doing quite well, but you can't see the difference. I mean, actually in this line of the red color, it has 5 colors in it, in there. But we can show that they are different by looking at the trace distance and then looking at the distribution of it. So as you can see, the first one, the Ito one, well, they're doing well, but we are doing better in the bottom one. So the maps, this one is the Ito ones, the Ruchons and the Guara-Weisman. They're doing quite well, but then we did better with the smallest trace distance. And then in this case, there's no Hamiltonian, and then also perfect measurement. And then we also tested with if we have the Rabi oscillation of the trajectories in there, and also if the measurement is not perfect, it's still doing quite okay. And this is for the SAT measurement. And interestingly, the result also matched with the analytical result here, where you can see that these two are the same, like the I and G, and then you can see the same thing here as well. For the fluorescence case, it's similar. These 3 are exactly the same number, and then also showing the same thing on the graph. So this is a qubit fluorescence measurement. Our method also did the same in these conditions that we showed. Okay, I'm gonna do like 3 more minutes for the last 2 slides. I think that's a perfect time. So how, like I have convinced you that maybe it satisfy the conditions that we set and is doing better in a numerical and also with the true trajectories and so on. But then we can also use it for the application. Because if you want to try to find the parameters or parameter that govern the dynamic of the system, you need a model that has no error, or at least the least error that you could do, right? So we can use our map with the least error, we believe with the least error, to try to come up with a parameter calibration of the experiment. You have an experiment, you don't know the parameter of it. You could use the signal and then just process the measurement signal with our map, and then you can come up with a parameter which is unknown. And this can be done online because you can keep measuring it and then feed the signal into the map and then comes at the parameters that we want. I'm not going to talk about much in detail, but the technique is a sequential Monte Carlo, which use a lot of Bayesian estimation. And the result is beautiful. It's convert the parameter estimation quite well with a map that we have. And then here is a nice result of, well, like in the experiment, you would want to say the parameter is fixed for the whole time. But with this method, you could kind of say, or you can see that the parameter in experiment are changing over time. And with this, you could do kind of tracking how the parameter changing over time as well. So this is the time scale of seconds, which in the superconducting qubit is in a nanoscale. And so basically it's like millions of data that can basically tracking the parameters changing in time. So I think with that, I'm gonna end with the conclusion, and hopefully this is a interesting talk for you guys, and thank you for your attention.
Thank you for a very nice talk, very nice results. Questions, comments?
The very nice talk. Maybe you said it, but I might have missed it. So are you happy with the second order in DT, or did you check that like at higher order? With your new method, so you showed how like you have new terms in DT squared.
Am I happy?
I mean, do you think that you need like to correct it like further to include like higher order, or looking at, because you stopped at the DT
second
squared?
order. Yeah.
So
I think I would, I would answer this way. You can keep to like third order and so on, but then the map will get just like keep growing, right? And I think the question should be like, when should I stop? And I think that depends on the dynamics of the system. And let's say that you have an experiment and you have to look at it and see what's the time scale of the data that was required by the measurement, right? By the setup, whether like how big it should be or how small it can be, let's say, in order to make the Markovian assumptions and white noise still satisfy, right? And once you have that number, that can be compared with the dynamic of it. For example, how much is the Rabi oscillation in that case? And that two number can help you choose which order to go and then what error that you can accept, I think.
Hi, thanks for the excellent talk. So, so in the last you showed that the parameter. So in the last you kind of showed that the parameters are kind of drifting, right?
Yes.
Yeah. So, hi. Yeah. Wouldn't this kind of make the whole like? But you're still kind of doing it in the level of the stochastic master equations in some sense, right? Or like what I'm trying to say is if the parameters are changing, wouldn't it be the map just becomes very non-Markovian or something?
Oh, no, the map is still Markovian. It is Markovian by the fact that the data that was acquired, the signal, was acquired with a delta t that is long enough for the Markovian assumption to be still valid, and that is okay. So this one, I'm telling you in a much longer time scale. So you're sampling the data with the delta t, but you're doing long enough, and then you keep measuring it for, let's say, a few seconds, which is quite long, and then you use that signal to plug it in the map, and then the map the map, in the map would have the parameters, right? You assume some parameters in the system, and then you can use that map to come up with like what's the best parameter that fit the data.
Okay.
Does that make sense? And then we can show that the parameter is actually changing over some time during the measurement. Yeah, yeah.
I see. Okay. Thank you.
But I mean, the interesting point for this is that we don't know how to check it, because in experiment there's no way to actually measure the parameter, right? If they have a way to check the parameter, we don't need this. Yeah.
Okay, yeah, please.
Yeah, go ahead.
Sorry, just a follow-up question, like from this slide. I'm just curious, like what are the two error bars, and we see the variance is kind of decreasing over time in this C plot, and so if we keep on increasing the number of trials, it doesn't go to, it saturates like that.
I see. Oh, okay. So this is a detail that I did not say much, but it's related to the Bayesian estimation. So the Bayesian estimation do the calculation by more data will help you like fine-grain the error bar for the parameter. So that's the error of the mean.
Okay, the blue line.
Oh, sorry. The red one is the error of the mean. So the error of the mean tells you how confident you are with the estimator.
So the estimated parameter is limited by the error there, if I may understand.
Yeah.
Okay, thanks.
I have a question, maybe it's my misunderstanding, but you said that it's delta t squared, but in your expansion, if I saw correctly, you also multiply by the yi, which is itself order of square root of t. So maybe it's it's not exactly delta squared. I was a bit confused. When are you stopping?
This one, right?
Yeah, because you have delta t times y, but y is proportional to delta t. It's a stochastic variable. So the way I see it, it's higher than delta t squared. But
I forgot.
This
did I make a typo in my slide? Let's see.
I mean,
Whoops.
it's not a typo, but I don't think it's delta t squared because y is proportional to delta t squared, square root. But okay, I have a
I'll answer you. I'm just like, there's like delta t in here somewhere that is not clear yet. But believe me, that is a delta t square.
Okay. I believe you, totally, I believe you.
Yeah.
I have a different question. In Riskin's book on the Fokker-Planck equation, there is a theorem called Pawala's theorem, where if you start with the master equation and you want to reduce it to a Fokker-Planck equation, which is a low-order expansion, you have to stop at the second-order term. Because if you do anything beyond that, you'll get some problem with the positivity of the density in the classical world. So my question was in relation to your suggestion, can we go further? Is it actually true that you can go further? Did anyone prove that you should stop somewhere like in Pawala's theorem, or did you think about this?
Yeah, okay. So I think like in this case, if you think that this is an exact form and it has all the properties that you want, right, in this form, right? So that means we are only doing the expansion to second order. And then I think you can keep going with a higher order, and I should not break down anything. And then also, and that's the infinitesimal record, right? But if we are looking at this, where we are using the small m or the measurement or the cross operator for the dt, and then multiply together, and then keep the higher order, I think it should be still fine. This is just a belief. I haven't proved it yet, but I think like the more that we keep the higher order, we will get terms that has the record, but in a different kind of integrated record, which I think it might be related to Anton's work, where when it gets to like a higher order, it needs a lot more correlation between the infinitesimal record. But yeah, I think we haven't tested yet to the higher order, but so far we think that we should be okay. But I would like to understand on your perspective on focal Planck as well.
Further questions? If that's not the case, let's thank
Lunchtime.
Areeya and all the speakers of this session.
Thank you.